The other question that we're going to see when it comes to covalent bonding is it polar ionic, polar covalent? Is the molecule polar? And so the two things that we're going to look at here is bond polarity and molecule polarity. Okay, so there's two different things, bond polarity and molecule polarity. Bond polarity is just whether or not any of these bonds, for instance, this one between carbon and hydrogen, that one between carbon and hydrogen, this one between carbon and chlorine, any bond in a molecule, we just compare electronegativity, and we can determine using our periodic table on the back of the periodic table, or the periodic table that I gave you in the folded over chart, what the electronegativity is and whether it is in the covalent section, the polar covalent, or the ionic section. So let's do some examples of that. I'm going to clean this up a bit just so we have some room, because I'm going to need some more things. But we're going to talk about molecular polarity. Just erased my line, that's okay. And bond polarity. So first thing I'm going to look at the CH4 molecule right here. In bond polarity, all I have to do is compare the electronegativity of anything in one bond. Now the key here is I have to check each bond individually. So I'm going to look at that bond right there. Well, that bond is between carbon and hydrogen. So I'm going to go to my periodic table, which I have here, and I click on carbon, electronegativity. Carbon's electronegativity is 2.55. You would look on your periodic table on your folded over charts, and you would see that the electronegativity for carbon is 2.55. Go over here to hydrogen and click on it. Hydrogen is 2.20. You would look on the back, you would find out that hydrogen is 2.20. Once I figured that information out, this big X symbol is called chi. That just means electronegativity. I don't even mind if you forget that, but it's good form. We always put the difference of the higher one minus the lower one. So carbon was 2.55 minus 2.20 gives me a difference of 0.35. Well, what do I do with this information? Well, once I have that information on your periodic table, on the back where you find the electronegativities, you have the chart up here that says percent ionic character. And in it, we've divided it. We said from 0 to 0.5, from 0.5 to 1.7, and 1.7 higher. This area, covalent. This area is polar covalent. And this area is ionic. So if you haven't put that on, you want to make sure you put that on your chart so you know that. So I look at my difference, I found it's 0.35, it falls into this range, so this is covalent bond. There is no unequal sharing. The electrons are going to be found basically right in the middle of this bond. There's no delta plus, no delta minus. I have to look at this bond next. Well, luckily it happens to be between carbon and hydrogen. I've already done it, 0.35. This bond is carbon and hydrogen, 0.35. This one is between carbon and hydrogen, 0.35. So I check each bond individually. It just so happens that all of those bonds are the exact same bond, and they're all covalent. So that is covalent bonding. So that's covalent bonds. I come over here. This one here, I'm going to look at that. I'm going to find electronegativity for carbon and for hydrogen. I already did that. 2.55, 2.20, 0.35. This is the same one. This is the same one. So if it's the same one, I don't need to do any more work. But I come over here and all of a sudden, uh-oh, that bond is a different bond. That bond is between carbon and chlorine. So I need a new electronegativity. I need to know, and I don't know which one's higher, so I better go look. So I'm going to go look. Come on, pen. Look. And I find that carbon was 2.55 and chlorine, ooh, it's 3.16, so chlorine is higher. So I'm going to come over here. The higher one goes first, so chlorine minus electronegativity of carbon equals 3.16 minus 2.55 equals, those numbers don't rattle off in my head well, so let's come back here. 3.16 minus 2.55 0.55, 0.61. I was going to guess about 0.6, but 0.61, 0.61. 0.61, if I look at my chart here, is above 0.5. That should be a point there. It's not a clear point. But it's less than 1.7, so it falls in right about here in my polar covalent range. So that bond is a polar covalent bond. Polar covalent bond. If it's a polar covalent bond, as soon as you identify it in this range, that means that this is not an equal shared bond. It means the electrons are pulled towards one atom more than the other, and it's always the atom with the higher electronegativity, which is chlorine. So chlorine is 3.16, means the electrons are more over here by the chlorine than they are by the carbon, which means that carbon is kind of positive. It's kind of missing electrons. And that chlorine is, let's use actually a different color for that. I'm going to use this green color so we can see it very easily. So that's kind of positive. That's kind of negative. And that's just for this bond. It doesn't mean that this is unequally shared, or this, because they're not. They were all perfectly covalent bonds. But that red one is polar, and so the carbon is kind of positive because the electron that should be here is shifted a little bit over here near the chlorine. So that's how we come up with the bonds. Are they polar or covalent? We just check electronegativity, and depending on the range it falls in, it's either covalent or polar or ionic. And if it is polar, that's the only time that we have to put those delta plus and delta minuses. So that leaves us with, is the molecule polar or non-polar? Well, once I've done all my electronegativity, I've looked at every single bond differently, and it would be fine if I gave you 4 completely different bonds. You do 4 different electronegativities and decide if they need to have polars or not. Once you're done, and you have put the delta pluses and delta minuses if you need them, you go and you look for them, and you try and find an area of the whole molecule that would be different from another one. So this molecule has kind of a diamond shape or something. So I'm going to try and look for an area somewhere that is more negative or more positive than any others. Well, this one doesn't. This and this and this and this, they're all equally shared. This area and this area, this area, this area, there's nothing on this molecule that looks any different than anything else. And so this one would not, it would be not polar or non-polar because there's no area that's any different. Molecule. This one, however, if I look at it, I'm going to get a different color here. What color am I going to use? I guess I'm going to use gray because that's all I see there. I'm going to, oh wait, color wheel. Oh, I like that. It's an ugly orange color. Go with fuchsia. Fuchsia color. Well, this area and this area and this area, they're all hydrogens. This all looks the same, but this side of the molecule here is different than this side of the molecule here. This side has a chlorine with delta minus, and this side has an H and nothing. So this area over here, this whole side would be kind of negative. And that means that this side, because this side is kind of negative, even though there's no delta plus, the delta plus is the bond, the delta plus, which is near the carbon. But this side will be less negative than this side, so that side would be kind of positive. This would have poles, just like the Earth has poles, the North Pole and the South Pole. This molecule has poles. It has a kind of positive side and a kind of negative side. So this would also be a polar molecule. And so I've determined that the molecule itself is polar because it has sides.